So in today's lesson, we're going to be tying together some of the things that we've learned about function behavior as related to the first derivative and second derivative, and we're going to kind of tie it all together in one polynomial. So we're going to be looking at the function f of x equals x to the fourth minus 4x cubed plus 2. And the first thing that we are going to do is we are going to identify the critical numbers of that function. And if you'll remember, the critical numbers of a function are where our function is either, a derivative of the function rather, is either equal to 0 or is undefined or does not exist. So to find the critical numbers, first we'll need to find the derivative of f. When we take the derivative of x to the fourth, we'll have 4x cubed. When we take the derivative of 4x cubed, we'll have 12x squared. And when we take the derivative of our constant 2, we'll have 0. And so we need to know, where is this derivative equal to 0? So to solve that, I think the easiest way is going to be by factoring. We can factor a 4 out of both terms. We can also factor out an x squared from both terms. If we factor out a 4x squared from the first term, then we have x. And if we factor 4x squared out of the second term, then we would have 3. So now that we have that factored, we could take each factor and set them equal to 0. So this would mean that x squared is 0. So then if we take the square root of both sides, x equals 0. Here, all we'd have to do is add 3 to both sides. We get x equals 3. So we can conclude that this function has critical numbers at x equals 0 and x equals 3. Notice that our derivative is a polynomial. It's a cubic function. And so there isn't going to be any value of x that would make our function not exist. It's defined for every value of x. So in this case, we don't have to check for where the derivative does not exist because it would exist everywhere. But if there were places where perhaps the derivative is undefined, then we would need to take that into consideration and find those points as part of our critical numbers as well. So now that we have our critical numbers, we can go ahead and move on to part B. Part B wants us to find the intervals where f is increasing and decreasing. So before I showed you guys a number line, and I still think that that's the easiest way to kind of organize your thoughts, but remember that the number line alone isn't justification. So once we take this number line and use it to figure out where the function is increasing or decreasing, we'll need to state that explicitly and why we know it's increasing or decreasing on those intervals. So we're going to look at the sign of the derivative to tell us where our function is either increasing or decreasing. So we need to include our critical numbers, 0 and 3, on this number line because those are the points where the derivative could change sign. And again, remember, we don't necessarily have to know the exact value of the function in each of these intervals. We just need to know, is the derivative positive or is the derivative negative? And that will tell us everything we need to know about whether or not it's increasing or decreasing. So for example, if I plug in a value that is less than 0, a negative number, here I would have 4x squared. Well, regardless of what the number is that I plug in, the x squared is going to be positive or 0. So this piece will always be 0 or positive. So really it's going to be this piece that's going to determine the sign of the derivative. If I plug in a negative value, say like -1, and subtract 3, I'm going to get a negative value, which means I'd have a negative product, a negative factor times a positive factor, which would give me a negative product. If I plug in a value between 0 and 3, again, my first factor of the derivative, 4x squared, will be positive because of the x squared. That would take care of any negatives. If I plug in a value that's less than 3, say like 2, then this factor is going to give me a negative value. So again, I'll have a positive factor times a negative factor is going to give me a negative product. If I plug in a value bigger than 3, then my 4x squared is still going to be positive, but now my second factor, x minus 3, is also going to be positive, because if I plug in a number that's bigger than 3, say like 4, we're going to get a positive. So we have a positive factor times a positive factor is going to give us a positive product, which means that in this region, my function is increasing. In this region, my function is increasing. I said that backwards. Scratch that. Negative, this region is decreasing. This region is decreasing. And this region would be increasing. So we can say that F is decreasing, where X is less than 0. And also for all of the X values that are between 0 and 3. And we know that because the first derivative of F is less than 0 or negative in that region. Again, you need to specifically state how you know based on the sign of the first derivative or whether it's greater or less than 0. We can also say that F is increasing for all X values that are greater than 3. And we know this because that is where the derivative is positive or greater than 0. So again, the number line is a great way to figure out where you're increasing or decreasing, but remember that the number line alone is not justification. You have to explicitly state the intervals and why you know that it's increasing there based on either the sign of the first derivative or whether or not that first derivative is greater than or less than 0. Now that we know that, we can use that information to determine the relative extrema of F. We know that at 0, our function is decreasing, and then after 0, it continues to decrease. So since we don't have a sign change at 0, which is one of our critical numbers, we know that that is not going to be a extrema. However, at 3, our function changes from decreasing to increasing. So if we have a critical number, and at that critical number, our derivative changes from negative to positive, then the first derivative test tells us that that point is going to be a relative minimum, provided that that point is defined on our function. And again, since our function is a polynomial, it's defined at every point. So we know that that point will be a relative minimum. So we can say that there is a relative minimum at x equals 3. And we know that because the first derivative of f changes from being negative to positive. And again, it's our first derivative test that gives us that information that we're applying there.